All right, this is Dr. Granier, Bio 208, Chapter 19. So we're going to talk about blood. Our first unit in our Bio 208 class is our cardiovascular unit. So we're going to start with blood, since blood, heart, and blood vessels all fall into the cardiovascular system. Blood is the fluid that's transported through the vessels, carrying within the watery part of blood nutrients such as amino acids, ions, water, sugar, but it also has cellular components. The cellular components of red blood cells are then binding and carrying oxygen, as well as some ability to bind and carry waste products. And then we have other white blood cells that are hitching a ride maybe from the bone marrow where they come from and heading to tissues that they'll take up residence and then fight the good fight from there. Or they're circulating white blood cells that plan to remain in the bloodstream and only hone into injury sites based on the chemical markers and signals that come from an injury happening to cells and tissues. All right, so that's kind of what we're going to focus on. The first part, let's focus on blood and what exactly is blood. It's cellular versus its non-cellular components, and then we'll dig deeper into all of those pieces and parts. Just because we have to review the goal or the objective related to Chapter 19 in all of the cardiovascular system in general is that you have to learn what is exactly in blood, what is exactly the heart, what is the physiology behind it, and then we'll get more of the anatomy completed in lab. Okay. So from the first picture in your book, and one of the first things we do in lab is we want to take blood from the body. And when you take blood from the body and you look through it, it's a dark liquid that you cannot see through. All right, and that comes from the fact that there are cells, which are large objects, suspended in the fluid background of blood. If we look at it as a tissue, remember that it is a connective tissue, meaning there is a non-living component that serves as a extracellular background matrix. That is the plasma, that is the water of the blood. And the cells, which are white blood cells, red blood cells, live within this non-living extracellular matrix. And they then reside and get nutrients and interact with the matrix to osmosis, move water in and out of the cell, and then transmit things into and out of the cell through the semi-permeable membrane. Okay, so one of the things we can do to start to take whole blood and separate it into its components is we can centrifuge it. And remember from physics that centrifuge is a circular force, and as you spin something for a period of time under those circular forces, things that are heavy are going to move towards the bottom of a tube, and things that are lighter will move to the top. So by centrifugal force, we can start to separate things that in the blood that are heavy, such as cells, from things that are very light, which would be water molecules and ions and small molecules embedded in the non-living matrix. All right, and when we do that, that gives us some very important information. It lets us kind of tell in general how much of blood is matrix, plasma, versus how much of blood is living or formed elements, living cells and their components, like platelets, which are technically not cells. And so when we look at that material, we can then see that blood is usually a little bit more on the plasma or the non-living side than it is on the living cell formed element side. And if you look at blood as whatever amount of blood you pulled out, let's say you pulled out 1 milliliter of blood, and then you spin it to see of that 1 milliliter of blood, how much of it is formed elements and cells versus how much of it is non-living extracellular matrix background plasma. You can basically say a percentage. 60% of the blood is plasma, extracellular matrix, water, background with material embedded and suspended, and 40% is the formed elements. And when you refer to blood broken down into that percentage of a certain amount of blood that you pulled out, that's known as the hematocrit. Okay, so hematocrit is almost always a percentage, and it represents the fraction of a whole blood sample. So the whole blood sample could be a milliliter, it could be 5 mils, it could be It could be half a mil, so it could be a micron, it could be a small little droplet. And usually what happens is our blood is uniformly suspending a certain amount of cells and a certain amount of extracellular plasma. And so whether I take a mil, 5 mils, a pint, a gallon, or I take just a small little 10 milliliters, typically when I get for a fraction of plasma versus formed elements, so what I get for a percentage of the plasma versus the cells is pretty much uniform throughout. And that again is the hematocrit, okay? Now, when I look at whole blood runs a little warmer than your body temperature. So we normally say human body temperature is 98.6 degrees Fahrenheit, which is about 37 degrees Celsius. Blood runs a little warmer, and that comes from a few different things. First, there's a little bit of friction. There's a little bit of energy and heat being generated from the fluid moving through pipes. Okay. Second, blood is picking up heat from cells that are doing a lot of energy expenditure. So they're picking up heat from muscle cells. They're picking up heat from any active bone cells or nervous cells or digestive material cells. And all of that heat is picked up by the water of the blood and then usually moved to areas of the body that are cooler, and that heat can then dissipate. All right, so blood is going to run a little bit warmer than your normal body temperature. All right, now if I look at a droplet of water, it has a certain viscosity, a certain kind of thickness to it. And water is pretty much lightly viscous because you can see through it. There's not a lot of things usually suspended in pure water. Right? If I make Kool-Aid, Kool-Aid has a little bit more sugar, a little bit more dye embedded and suspended into the water and around the water molecules. So Kool-Aid is a little more viscous than water. If I put a little bit more material, I might make Kool-Aid now into more of a jello or a slime or a pudding, and that becomes even more viscous because now I'm embedding between water molecules more materials and sugar and dye and molecules, and it's making the water move from very low viscosity to very viscous because it's beginning to not really be water anymore and kind of become more of a jelly or a putty type substance. So blood is going to fall in the range of, it's not pure water, it's not Kool-Aid, so it has a little bit more viscosity than those things, but it's not quite all the way to jelly or slime or jello pudding, okay? So its viscosity is a little bit more than water, 5 times more than water. So when you look at blood, because there's more material suspended between the water molecules, it's not something you can see through, all right? If it was more like water and less viscosity, you would actually be able to see through it a little bit easier, okay? Water has a pH, so if we do pH paper on water, it should have a pH of about 7. So that means the number of free hydrogen ions suspended on that logarithmic scale or the certain amount that it registers a 7 on the pH scale. For blood, there are less free hydrogens. So the hydrogens that are suspended independently in the water of the blood, in the plasma, are going to be less numerous than what you have in pure water. And because of that, on the pH scale, it's going to rise from 7.0 towards 7.1, 7.2. It's actually going to be at 7.4, which is defined by pH in chemistry as an alkaline number. All right, we don't want it to get all the way to 8 to be more of a pure base. We want it to be slightly alkaline, so we keep it 7.4. Now, men are naturally a little bigger than women because I think the average male in this country is like 5'11", and the average female in this country is like 5'4", 5'5". So just because of the natural ability of men being bigger versus women, men typically have 5 to 6 liters of blood in their body, and women have about 4 to 5 liters of blood. Now, if I take a 5'4" male and a 5'10" female, it might be reversed, but again, we're talking like population averages, right? If you take all of the blood, so if I was to take all of the blood out of my body, it is water, it has cells in it, and I would be taking about 7% of my body weight. All right, so if I need to lose a quick 7% of my body weight, suck all the blood out of it. All right, you probably won't live, but you'll be 7% lighter. Okay, now that's whole blood. We need to get to the nitty gritty. So we need to get in the weeds. So the first thing we want to do when we get whole blood in a lot of cases is we want to find what exactly are the cellular parts and how much of the cellular parts and what kinds of cellular parts are there versus what are the molecules, the hormones, the proteins, the different items suspended within the water and the non-living background, the matrix. So the way we can do that is first get whole blood and then spin it in a centrifuge. And spinning it in a centrifuge, again, will separate everything in the blood by weight. All right, it'll get all of the heavy cells, which are heavier, which are bigger molecules. Again, they have phospholipid membranes, they have organelles, they have DNA, they have RNA, they have lots of proteins inside of them. So they're a lot bigger entities than your simple glucose, which is 6 carbons, 6 carbons, 6 oxygens, and 12 hydrogens. It's a lot, your cells are a lot bigger than your amino acids, which are maybe 3 or 4 carbons and some nitrogens and some oxygens, so small molecules, all right? And so we separate first our whole blood into the plasma versus the formed elements. Now, that plasma is still a mixture of water molecules, and it's mostly water molecules. So it's about 92 to 93% water. So if I was to try to take 100 marbles from plasma, and those marbles represented everything that was suspended inside the plasma, 93 of the molecules would be water molecules. So they'd be H2O molecules. Okay. The other 7% of what's left, or 8%, because 92 minus 100 minus 92 is 8, can be a lot of different items. Mostly it can be proteins. Proteins such as albumin, proteins such as let's see, some hormones. So for females, you might have some LH or FSH circulating from your brain towards your ovaries. You might have your growth hormone circulating in there. You might have some other proteins hitching a ride in your system to get to your brain or get to your muscles or get to other areas of your body to do communication or just be a fuel, be a you know, a useful molecule. All right. The other molecules that make up that small 1% are, again, lots of different items. You need solutes, so that's what they're called. You need electrolytes, so you always hear about people get cramps because their electrolytes are low. Sodium, potassium are 2 of our most common electrolytes, but calcium, magnesium, zinc, copper, I mean, those are some of the other. Iron can also come into play with that. Other organic solutes, of course, we know with people who are diabetic that glucose is going to be found in our blood. So glucose can be there along with lactic acid. If you're an athlete and you've just finished a workout and I pull blood from you, I'm looking for a small carbon molecule known as lactic acid. Amino acids come into play here. Some small free fatty acids might be there. And then there'll be other organic molecules that might be waste products. So bicarbonate, uric acid, keto acids, and a bunch of other molecules, again in chemistry, that come from processes where cells make or break molecules that they use inside their organelles or inside their membranes to do certain metabolic processes. Okay, so most of the plasma, again, is water. So when we actually separate whole blood into plasma versus formed elements, you almost can see through plasma. You still see a little bit of cloudiness because, there's some things suspended like proteins and ions and small molecules, but you're beginning to get more clarity because you're getting closer to being almost pure water. Now, the formed elements, the cell parts, are going to be mostly red blood cells, all right? So again, if I have 100 cells, typically in a sample, 99 of them are usually going to be red blood cells. One will either be one of the many types of white blood cells or maybe a platelet. Okay, so if I was to try to, again, take a sample of your blood and look at your white blood cell counts, sometimes I need more than just a small little droplet of blood. I need probably a good milliliter or two. That's why sometimes when you go draw blood, they get those huge tubes and they take, a good milliliter to 2 milliliters of blood in the tube when they stick you, and it's because they're trying to get a large enough sample so that way they get a nice sampling of white blood cells. Granted, they're taking lots and lots and lots and lots of red blood cells, but their goal is to sometimes get a large population of white blood cells so they can see if there's some abnormalities to those cells or increased numbers of a certain type of cell that shouldn't be that high in number. Okay. Now, I would say that every one of you needs to be able to fill in this flow chart that's presented on the slide. So I would say everybody needs to be able to fill in the numbers here and be able to provide examples of everything. All right. So when I take whole blood, initially, when I separate it, I want to separate it into its living and cellular components versus non-living. So its background material, its plasma. In general, plasma is usually a little bit more than the formed elements. Again, if you're an elite athlete, you might be 50-50. If you're blood doping and you're jacking yourself up with extracellular or with cells coming in through a blood supply because you're, again, doing illegal things to become a better cyclist like Lance did, Lance Armstrong, this is what he got trouble for. Maybe you might get to a place where the formed elements are 53 or 54% and plasma is on the lower end, but that is not normal, okay? So we normally see plasma 60, 55%, and the formed elements 45% to 40%. Okay. In females, because of the lack of testosterone, testosterone tends to increase red blood cell numbers. You might even dip to your red blood cell count is 37%, or your cell numbers are about 37-38% of whole blood, and your plasma is almost up to that 66 or 63%. Okay, so again, there's a little bit of fluctuation, there's a little bit of a range, and some of that comes back to athletic conditioning, altitude training, blood doping, hormone treatments such as testosterone or even EPO, blood hormone treatments. Okay. The next level, again, plasma is mostly water, but there are things suspended in the plasma. The majority of those things suspended in the plasma are proteins. Some of those proteins we're going to learn are vastly important in transport. Okay, transport of lots of different molecules, because some molecules do not like to be in water. And since blood is mostly water, they need to be bound to proteins to be able to hitch a ride. So triglycerides, testosterone, estrogen, cortisol, aldosterone, thyroid hormones. All right. All of those hormones, I need testosterone, I need estrogen, I need cortisol when I'm stressed. I am going to need triglycerides. I'm going to need cholesterol and fats to get to my cells for energy. Well, they can't just hitch a ride very easily in water because they are hydrophobic, and water is hydrophilic. So part of what I have all these proteins for in my blood is to help bind them, those hydrophobic, those fats, those molecules that do not like to be in water. If I bind them to a protein, the protein can make them a little bit more massed, a little bit more easily carried in water, and so then I can transport them to different areas of the body. Okay, that's why there's a lot of proteins. The other big number of proteins is because you have antibodies. You have these proteins that their whole reason to exist is to identify pathogens. So pathogens can be viruses, can be bacteria, can be worms, can be ticks, can be fungus, can be amoebas, can be single cellular organisms, variety of things. Anything that's trying to take over and grow and propagate, and it is hurting or damaging me is a pathogen. All right, so a lot of my proteins are going to be these antibodies that exist to help tag, kill, and destroy pathogens. All right. And then there are going to be another group of proteins that are in my system to help with a clotting process. In the event that a burst, a damage happens to the circulatory system, those clotting proteins, main one being fibrinogen, can start to plug the hole so that way the minimal amount of blood loss occurs. Because again, as a woman, I only have 4 to 6 liters of blood, so I don't want to bleed it out. And in men, I'm 5 to 6 liters. All right. You'll have a small amount of other proteins again. My growth hormone, my LH, my FSH, my prolactin if I'm making milk in my breast, so all of those other hormones, all those other signaling molecules. Okay. For the other solutes, again, we know that glucose, we know lactose, sorry. We know that we have other sugars, fructose, we have lactic acid. They are going to be suspended in our system. We know that amino acids are the building blocks for proteins, and when we take in amino acids, proteins in our food, we break them down, we bring them in as amino acids. They circulate to cells so they can be rebound into proteins. We know nucleic acids come in and we take them up so we can make more DNA, more RNA if we're going to replicate a cell or if we're going to express genes or we want to make more ribosomes. All right, so there's a lot of other molecules that are organic because they have a carbon and a hydrogen atom in their chemical structure. So they are going to be suspended. We have a lot of waste products, bicarbonate, uric acid, keto acids, a lot of acids that come from the process of making energy. So you are a little acid making factory, and a lot of those acids need to get to the kidneys so they can then be pulled out, and this is why urine is so acidic, because it's where all those metabolic acids, those waste acids that you made in a lot of different cells, end up. So we don't have acidic bodies and acidic blood. Right? And then your electrolytes are important because electrolytes, we're going to learn, are how we conduct electrical signals in our body. And so having the ability to conduct electrical signals comes down to we need a certain amount of positive and negative ions in certain places inside and outside the cell. And we need them to be in a certain amount. So we have wanting to flow by concentration and by electrogradients. And so as things happen and electrolytes get lost because we need osmosis to occur and water to be pulled in different places, we can replenish them from our diet and then putting them in our blood and carrying them to those areas of our body. All right. The formed elements, again, 99 out of 100 cells, if you do a cell count, so if I take a droplet of cell and I count 100 cells, 99 of them are typically going to be red blood cells. They are the most abundant cells in the blood. That other cell, it can be a variety of white blood cells. And again, some of these white blood cells are just hitching a ride until they can get to their final location and take up residence, whereas some of them are residents of the bloodstream and plan to stay and circulate. The other potential would be a small cellular component that has broken off of what was maybe at one time a big mega karyocyte, and those are your platelets. And they're with the clotting proteins circulating, so that way in the event that a catastrophe, a break, or something happens, they can help form a temporary and then a permanent plug until the vessel can heal itself. Okay? So another picture, again, just to try to highlight how whole blood is divided, and then further how plasma becomes mostly proteins, a few other solubles, and then water. And then formed elements are mostly red blood cells, and then that one other cell is going to potentially be either one of the white blood cells or the platelets. Okay. And again, key things, we know we have to get glucose to the brain. So yes, something in the plasma needs to be glucose, fructose, lactic acid, right? We know we need to get amino acids to cells that are going to express genes, because what is the eventual product of many of our genes? A protein. Well, how do I build a protein? I take a tRNA at the ribosome that's bound to an amino acid, and I get it in the right order because the messenger RNA tells me to do it that way. So I need amino acids. And then a lot of those organic wastes occur because once I eventually break down a fat, break down a glucose molecule, I generate acid waste, and I'm going to need to get rid of it. Okay, so a different slide just to again highlight what are the blood plasma components, all right? And then here again, for our formed elements, most of the formed elements, most of the cells are erythrocytes, blood cells. Now, I've been very careful about saying cells, formed elements, some non-living material, because part of the reason we can't say these cells are truly living cells is erythrocytes no longer have a nucleus. And so by definition, if you go back and look at cells in chapter 3, cells normally have a nucleus and their organelles, and they still have the ability to undergo mitosis, which is cell division. Erythrocytes are terminally differentiated cells that are no longer able to divide, and they're no longer able to respond to a few issues because they no longer have a nucleus. All right, so technically speaking, they're kind of like dying cells because they're slowly undergoing a process of losing their organelles. They've lost their DNA. They're going to survive a little bit longer, about 120 days, but they're on a road to death. All right. Platelets are also another component that are technically not cells. One cell, a megakaryocyte, splits and fractures into these small components and pieces. Now, it still has a membrane, so it still has phospholipids, it still has proteins embedded in the phospholipids, and inside the cytoplasm of a platelet, there's still some glucose, there's still some proteins. So there's still some metabolic processes that can take place, but technically speaking, a platelet is not a cell. It doesn't have a nucleus. It doesn't have the ability to undergo mitosis and divide. Okay, so that's part of the reason why you don't call the living part of blood the living, you call it the formed elements, because red blood cells are on a pathway to death, and platelets are also somewhat not living cells anymore. They're on a process of a cell dying. White blood cells, however, can still undergo mitosis, they still have their DNA, they can still respond to stimuli. So they are, in a sense, the only living and thriving pieces of formed elements. Okay. Now, if I take a droplet of blood from a male and I take a droplet of blood from a female, because males have testosterone, and testosterone is normally pushing muscles to need to be building, that's why it's abused by athletes, because it builds muscle. And building muscle means I need amino acids, I need energy. Testosterone tends to push red blood cell counts higher than in males than in females. So what that means is a droplet of blood for a male is going to have a higher number of red blood cells. So 4.5 to 6.3 million red blood cells are suspended, typically in a male, in a microliter of whole blood. All right, and a microliter is a very small amount. Females don't have the testosterone to the same degree, so they don't have as much protein synthesis going on. So their red blood cell count in 1 microliter is a little less, so 4.2 to 5.5 million red blood cells per microliter. All right. You can push those numbers if you go to altitude. You can push those numbers if you're an athlete. You can push those numbers if you take EPO. You can push those numbers if you get a blood transfusion of blood cells into your system. All right. Red blood cells represent, in some ways, oxygen carrying capacity. So if I have 5 million red blood cells in a microliter for a male, but I only have 4.5 million red blood cells in a microliter for females, technically speaking, if I ask that male and female to give me a 100-meter dash sprint, the males might be able to get to the finish line faster because they have more oxygen carrying capacity and more muscle mass than the females. And it comes back a little bit to that red blood cell count. So that's why the world record for men is like 9.5 for the 100 meters, and the women it's like 10.2. All right. There's a little bit of the physiology behind the number of muscle cells, but some of it also comes back to oxygen carrying capacity. Males have more. Okay. All right. Did I skip a slide? Yes. Somehow I skipped some slides. Okay. So let's talk about those red blood cells. So you need to fit in a teardrop. You need to potentially fit 5 million cells. How do I fit 5 million cells? Okay. Well, one, I'm going to make them small. So red blood cells are pretty small cells. So I can't see them with the naked eye. I have to look at them through a microscope. Second, I am going to make them to where they are stackable. So think about plates. Plates are pretty big items, but you can put like 20, 30 plates stacked on each other on a shelf. And they stack very nicely together so they can fit a lot of plates in a small space. All right. So red blood cells kind of take that hint of I am going to be small so I can fit a lot of my components in a small little volume or small little amount. And I'm also going to make myself very stackable. Now, the stackableness also enhances a second key element of red blood cells, which is I need the center of my cytoplasm at any point in the cell to be relatively close to my membrane. And the reason why I need my cytoplasm in the center, so what I'm talking about is I need all of this cytoplasm here in the center of the cell, in the midline area, to no matter where it is, if it's on the edge or in the center of the cell, it needs to be relatively small or a short distance away from the membrane of the cell. And the reason why I need that is because I want all of the protein, all of the material that is in my cytoplasm to be relatively close to the membrane, so that way if anything comes in or wants to go out, it doesn't have a very far distance to travel. All right. This is why red blood cells take on this biconcave disc shape. So it allows them to have a circular, stackable shape that also lets the material inside, the proteins inside, be relatively close at any point in the middle of the cytoplasm. It lets that protein, that material, be close to the edge of the cell for diffusion. And that's why we give the cells a large surface area to volume ratio. So if I'm right in the middle over here, I'm still pretty close to the surface area of the membrane above me, to the side of me, below me, and that gives me a large surface area to volume ratio. And that's an important advantage because if oxygen is coming and diffusing into the cell across the membrane, that means oxygen molecules will very quickly come into contact with proteins throughout the cytoplasm and get bound up by those hemoglobin proteins. Okay, so the red blood cell structure is small, so I can pack a lot of them in a small amount of volume. It's stackable, so I can further stack more and stack them up, and they can form what's known as these rouleau structures. They are biconcave, so they're almost donuts, but they don't quite have the hole made in the middle. And that donut helps make a biconcave disc for stackability. And it also helps make, at any point in the cytoplasm, proteins embedded in the cytoplasm or near the membrane of the cell, which gives me a large surface area to volume ratio. The last thing about the biconcave disc is it makes some flexibility. So when I have to maybe bend, when I get to a fork in a vessel and I have to pick right or left pathway, or I get into a capillary and I kind of go in at the wrong angle, and so I kind of get bent or shoved around, I have that flexibility as a kind of molecule or as an entity to not burst or not break, right? Our ceramic plates don't have that. So if I try to bend my plates, if I'm strong enough, I'll break it in half. The cells with their biconcave disc and their material made up of phospholipid bilayer with proteins embedded has some flexibility, so it has some bend. And that's part of the good thing that means my red blood cells are not, every time they try to hit a fork in the vasculature or head into a capillary and get bumped around, they don't explode, okay? Now, most of what is in the red blood cells is going to be a little bit of water, a little bit of glucose, a little bit of some enzymes, some proteins that help with the process of binding oxygen to hemoglobin and binding carbon dioxide and water together, so a carbonic anhydrase. But the majority of what is in the cytoplasm of a red blood cell is the protein hemoglobin, okay? So hemoglobin, I want to pack as much of this protein as possible in the red blood cell. Because I want to make most of my cytoplasm hemoglobin, I am going to get rid of ribosomes. I am going to get rid of Golgi bodies. I am going to get rid of endoplasmic reticulum. I am going to get rid of the nucleus of the cell. All right. And then when I give up all of that material, I'm doing all of that organelle kick out so I can give myself more room to pack more hemoglobin molecules inside the cell. Now, what is hemoglobin? It technically is 4 amino acid chains. So that means I make 4 messenger, or actually I can make 2, but I can make 4 amino acid chains, and then I make them into these alpha, beta, then entities, and I take 2 alpha chains and 2 beta chains, and I form a quadrary protein structure that is going to form a protein. So hemoglobin technically is 4 amino acid chains made into these alpha and beta chains that then come together, 2 alpha, 2 beta, and form a hemoglobin molecule. So it's a pretty complex protein. Now, each component, each amino acid chain, each alpha and beta chain is also going to have embedded within it a secondary part that is going to have an iron atom with some amino acids around it. And it's going to form what's known as the heme complex. And it's going to embed somewhat within each alpha and beta chain. And the heme part is going to be the critical part that has the ability to bind to oxygen. Each heme molecule can bind 1 oxygen molecule. All right, so the iron, which typically wants to become a positively charged atom, is going to have a positiveness. Oxygen tends to want to have a little negativeness, and so they're going to be attracted towards each other. And oxygen is going to bind to 1 oxygen molecule binds to 1 heme. So 1 hemoglobin protein has 4 hemes, so binds 4 oxygens. All right, so each hemoglobin is like a 4-seated car. It has 4 seats. It can carry 4 oxygens, 4 people. All right. Typically speaking, our goal with hemoglobin is to get every car with a driver. So every hemoglobin's first goal is to bind 1 oxygen. Once we get an oxygen bound to hemoglobin, we then try to get every car with a second oxygen with 1 passenger. Then we try to get every hemoglobin to then have the 3rd oxygen, and then every hemoglobin to have the 4th oxygen. Now remember that these are molecules, and by chemistry rules, they are in constant motion. So even though you technically have oxygen and heme, and the iron part of heme trying to bind to each other, for every microsecond, they are attach, unattach, attach, unattach, attach, unattach. And so every oxygen and hemoglobin is kind of oscillating with their molecules attaching and unattaching. So when we take a snapshot and a physical stop in time, and we say hemoglobin is 98% saturated, what we're technically saying is in that snapshot and window of time, that microsecond where we freeze everything, 98% of every single heme molecule and every single hemoglobin of every single cell has the oxygen bound to it in that given fraction of a second, and 2% of them have the oxygen and hemoglobin for that fraction of a second separating, because in constant motion they will separate and bind constantly. All right, and so that's why you never get to 100% saturation, because technically speaking, with molecules in constant motion, there's always that small little percentage in a given fraction of a second that might be, if you freeze it, separate and not bound to the hemoglobin. Okay, now if we look at this red blood cell, again, the whole goal is to get not one of these molecules, but to get millions and thousands of them suspended in the cytoplasm. And so one red blood cell can carry a buttload of oxygens because it has a buttload of hemoglobin molecules. One droplet of blood having 5 million red blood cells, with each red blood cell having thousands and millions of hemoglobin molecules, and each of those hemoglobin molecules having 4 oxygen binding sites, then do the math. It very quickly becomes a very small amount of blood has a very large amount of oxygen binding and carrying capacity. And so that's why, we can tolerate, when you're underwater, the air hunger and the oxygen drive to breathe is going to happen, but we can kind of like ignore it for a few seconds, because technically speaking, we still have a lot of oxygen bound in our blood. We still have a lot of hemoglobin bound with oxygen, and we can go a little longer before we completely exhaust all that oxygen and have to take a breath underwater. Okay? All right. I think I'll stop here. So for review purposes, at this point, your goal is to understand what is blood, the components of blood, what are the components of plasma, the different categories, the big one being most of plasma proteins are carrying molecules like albumin, or binding proteins for thyroid hormones, testosterone, and other fat kind of hormones. Then you have a large amount of proteins that are antibodies in our immune system that fight pathogens. Some of the other globulins are also some binding proteins. And then small amount of proteins are going to be related to clotting factors, and then just random growth hormones and other signaling molecules that hitch a ride through the bloodstream. All right. Moving to the formed elements, we've really hit on just red blood cells so far. Again, red blood cells are unique cells in that they do not divide. So they are cells that, in the process of being made, are going to get rid of every single organelle that is not part of its oxygen carrying capacity, and it's living for about 120 days. And it's going to then take its cytoplasm and try to fill it and maximize it with as much hemoglobin as possible so it can increase its oxygen carrying capacity. Hemoglobin, again, is a unique protein in that it has that iron part. There's 4 components to a hemoglobin, and each of them has a heme, and so one hemoglobin molecule carries up to 4 oxygens. And like a car, we tend to want to have all of our hemoglobins bound with one passenger, and then we add the second passenger. We don't go with 1 full hemoglobin and 5 empty hemoglobins. We try to everybody get 1, everybody get 2, everybody get 3, and then everybody get 4. And when we take off oxygens, we do it the same way. Everybody give up 1, everybody give up 2. So we always usually have 1 oxygen to 2 oxygens on a hemoglobin and on every hemoglobin. Again, for stackability, for making hemoglobin as available to bind to oxygen as possible, the red blood cell is biconcave, so it can stack, it can ram a lot of red blood cells in a small space, and it can make its surface area to internal volume, and then for hemoglobin availability as that ratio as optimal as possible, so it doesn't take a lot of time, it doesn't take a lot of energy, it doesn't take a lot of space for oxygen to then be able to come in contact with the hemoglobin. All right, so I will make a second video and I'll pick up on red blood cells and their life expectancy, so how we make them and then how we break them down. Okay, everybody, I will be getting that second lecture up hopefully tomorrow, and I will see you in class or lab.